Okay, this is 8-21. I've drawn a couple views here. Um, what would happen is you have this piece coming down like this. Now you have 600 coming down here, so we'll go ahead and put 600 going down. Okay, along this beam in here, say this section right here, you would only have P over A. You'd have 600 divided by the cross-sectional area because you have no moment being created. Once you start to move from here to the right, then immediately you're going to be creating a moment. And the moment arm is going to be the distance from the center of this to the distance you're going right. So as I start working my way across here, now the 600 across here is creating shear, but it's also creating a bending moment. And I work my way all the way over to here. Now once you reach this part of the beam and start your way up, you not only have P over A, 600 divided by the cross-sectional area across here, but it's also creating a moment. Now the maximum moment in this case would be 600 times 1.5, which would be 900. So we can go ahead and put that down. Max moment would equal to 900 foot-pounds. And that moment's being created this way. So if you tried to draw a free body diagram anywhere across this cross-section, anywhere across this length right here, what you would have would be the forces that are trying to resist it would be going this way. This would be 600. You would also be creating a moment that's going back the other way that's trying to resist it. And that would be 900 foot-pounds. Okay, so now I've taken an area right in here, and I'm showing it right down this view right here. So at this point, you would have 600 coming down, or sorry, 600 coming up. This is creating a moment that's bending it back this direction. So obviously this beam is going to have to resist that moment. So what you would have would be at this outer fiber right here, you would not only have P over A going down, you would also have the MC over I. So right in here, you would have maximum tension. And on the other side, since this moment's bending this way, it's causing compression here, and this would be a combined or minimum. You have to be actually call that the minimum stress. That'd be the minimum stress right there. Okay, so what's taking place? And we document this. This part right here, this would have P over A plus MC over I. This part here would have P over A minus MC over I. Alright, so let's go ahead and calculate what some of these stresses are going to be. Let's go ahead and get our area. We go back and look. We have a 1-inch radius right there. So using pi r squared, pi times 1 squared, that's going to give me a value of just pi, and that's inches squared. We'll get our I value. Our I value is going to be, what is that, 1/4 times pi times radius squared. That gives me pi over 4. Now our C max, as I look at the cross section, is going to be distance from here out to the outer fiber either way because it's symmetrical. So C in this case will be 1. So if I want to find the stress here, we'll call that point, let's see what we'll call it. We'll call that point B. and we'll call this point point A. Okay, so the stress at A, or stress at B, let's do the stress at A first. The stress at A is going to equal to 600 divided by the cross-sectional area, which we said was pi. And again, we're doing the A, and then we're going to do minus the moment, which we said was 900 times C, which is 1, time our moment inertia is pi over 4. Okay, when we run that number there, we'll get minus 13,600 psi. So what's happened is, since we got a minus here, we actually have the beam in compression at this location here. Alright, now we'll find the stress at B. The stress at B would be 600 divided by pi plus the 900 times the 1 over pi over 4. And when we run that number, we will get 13,900 psi. And that would, oops, that would be in tension. Okay, so if we drew just a view of what's taking place here, this being the beam, then what we would have in this area here, I'll slide this down just a little bit and draw a line to represent the stress. Oops, get just a plain old line. Then in this area here, you'd have 13,600 in compression. And here you'd have 13,900 in tension. Okay, so now we have this drawn. What we can do now is we can find out where this neutral axis is going to fall. The neutral axis, if I mentioned earlier, the neutral axis is where the stress is going to be 0. You have no stress. So the neutral axis does not run through the centroid. I may have called it the neutral axis earlier, but that was just talking about the centroid. If I want to find out where this point is, where I have no stress, then what I would do would be I have 13.9 coming this way, 13.6 coming this way. We know this beam here, do some black, is 2 inches wide here. It's the diameter. So we'll set this distance as x, so this is a 2 minus x, and this just becomes a slope equation. Rise over run is equal to rise over run. So can't we say 13,900 over so it's y, delta y over delta x is equal to 13,600 over 2 minus x. Cross multiply, we get 13,000. We'll just make that 13.9 to save some time. Times 2 minus x is equal to 13.6 times x. We'll solve that 13.9. That gives me what? 27.8 minus 13.9x is equal to 13.6x. Move this other side. 27.8 is equal to, add those together, what's that give me? 27.5x. Solve for x, and you get 27.8 divided by 27.5, and that gives me 1.01. And so that means if we go over 1.01 inches right here, then we've crossed 0. This line here has crossed the x-axis, so we would have 0 stress. Alright, hope this video helps.